On behalf of the NASA Glenn Research Center, I'd like to present my senior project, the design of a vacuum pump heat exchanger, or as it will be referred to for the rest of this, the VPHE. There are currently two Sullair V25-100 vacuum pumps in the basement of the wind tunnels facility at NASA Glenn Research Center, and because they are not Carnot brand vacuum pumps, they generate heat when they operate. The problem is that the HVAC system in the basement is already saturated just the way that it is right now. When I visited for the first time in September, it was 30 degrees outside, and in the basement it was 90 degrees. Because of this, the facilities people won't let the researchers turn these vacuum pumps on, as it would get dangerously hot in the vicinity of these pumps, especially during summer. This has delayed the experiments for many weeks, if not months. The project definition is as follows. Design something to allow operation of the pumps without heating the environment or negatively impacting the ease of use of the vacuum pumps. This includes maintenance, modification, and OSHA compliance. Oh, also, don't void the warranty on the pumps. Direct quote. The deliverables for this project include the following: architecture selection, conceptual design, and goal specification, meaning that my final design will need to be optimal in some sense of the word, and I need to define what that sense of the word was. The design specifications for the open loop heat exchanger, the critical design parameters and variables of the design, technical documentation, etc. I had to generate usable documentation and models as well, including subroutines for calculations that they could use for future design optimization. And I needed to design as smart of a SolidWorks model as possible to make the lives of those who needed to modify this design in the future as easy as possible. The project, the way it's laid out with its interdependencies / work breakdown structure, has 4 phases that need to be done in order. The first is data acquisition and problem identification. The fact that the preceding slides exist is proof that those worked out just fine. Conceptual design is the second. Phase 3 is thermodynamic modeling, and phase 4 is detailed design and technical specification, basically generating all the things that will go in a folder that I email to the folks at Glenn in the next few days. For phase 1, I had to get all the data on the vacuum pump and read all the manuals that came with it that I could. I had to construct piping and instrumentation diagrams for the systems, and especially the one main system, in order to determine the control volume and let me start thinking about what type of exchanging apparatus I could put in there. I had to determine the thermodynamic performance characteristics of the vacuum pump along with the locations of the highest thermal flux to make sure that there weren't just stagnant radiative hot zones that were going to have hot spots in the room anyway. I had to make sure the pumps still had warranties on them at all so that I could avoid, well, voiding them. And I had to check and make sure that if any OEM solutions to this problem existed, that I buy them and design for them. And these solutions do exist. I'll get to that later. Here's what the Gantt chart looks like. Worthy of note is that I didn't get concrete information on how good the purchased solution, the water cooling apparatus that just kind of clips onto the pumps that comes from the company Sullair. I didn't get any information on how good that was for months until after phase 1 ended. So stay tuned for that. But anyway, here's the P&ID diagram. There's cold water that enters the control volume that absorbs heat and then leaves as hot water. During this time, heat radiating from the vacuum pumps is added. The fan, which forces convection across the long and bendy tube, has a non-ideal efficiency, so it releases heat into the room as well. And the act of condensing the extremely moist air in the room at upwards of 95% relative humidity, from what I'm told, but just in the middle of dry September when I visited and measured with a hygrometer, it was 85%. This condensation of the moisture adds a relatively large amount of heat to the room because condensation is exothermic, and it's not negligible in the slightest, much to my initial surprise. Here's the details on when exactly the Sullair representative got back to me with the information on the purchased apparatus. He got back to me, it was the better part of 2 months later, and I have this information in appendix number 5 if you'd like to see it. But moving along to phase 2, there's conceptual design and critical parameter selection. Here's the Gantt chart of when and how this happened. This part took very little time. The conceptual design weighed various types of heat exchangers I could use, and not just architecturally, but or rather not just specifically with what type of pipe or stuff like that, but apparatuses and cycles as well. The first one was a thermoelectric cooler, and it was simple as all hell, and it had a very efficient heat exchanger. The overall heat exchanger efficiency was very high, but it was very expensive, and it was not thermally efficient in the slightest. The next involved compressing the air to raise its temperature before exchanging its heat, because you want a high temperature difference in order to achieve a high heat exchanger efficiency. But air is not a good working fluid for this at all for refrigeration cycle purposes, so it wasn't going to work. It was a lot of complexity and a very large air pump just to achieve not very high performance at the end of it. The most efficient cycle of all of these was that of using another working fluid, just like a refrigerator, to compress extremely hot, chill that, and then cool beneath what would have been the freezing point of water in order to get even higher temperature differences at all the steps in the process. But this was expensive, complicated, and extremely large. The datum that won in most of the categories for this straightforward use case was just uncompressed air and water, so that's what I went with. Moving on to phase 3, this was the most time-consuming of all of the phases. I had to perform the entirety of the thermodynamic modeling. It was the selection of a non-ideal model. I had to try and figure out what exactly the math was going to end up looking like. I had to collect design parameters about the pumps and size of the room as well. I had to validate my lemmas, which are intermediate assumptions and intermediate calculations. They're all the little equations used between the large calculation steps. I had to determine my structural parameters like hydraulic diameter ranges and plausible pipe lengths and maximum allowable exchanger geometry before it ran into the ceiling or needed to move a wall out of the way or something like that. And I had to spend a hefty amount of time doing the optimization for all of it once I was done, but it came out to look like this. As you can see, this took the gross majority of 2 months. But here's the calculation that I got out of it. Here's the calculation more specifically for the air that's flowing across a bank of cylinders in crossflow. You have N sub T tubes vertically, and you have N sub L tubes lengthwise, and they have diameter D and spacing S sub L and S sub T. There's nothing particularly exotic here, other than the fact that some of these tables may look a little bit complicated. I have more on these in my scripts at the end if you'd like to see some more examples. For the pressure drop from the fan, I originally used just cylinders in series, but it gave vastly different answers from what other models I found were getting. So I ended up using the pressure drop model from Zukauskas, the same place where the Nusselt number calculation on the previous slide came from. And that compensated for the nozzling of the air, the increased velocity of it, as well as the turbulence that started to occur after subsequent numbers of pipes in a row. And it also compensates for the different Reynolds numbers from the friction factors, as you can see right there. Also, G max is the minimum velocity of the working fluid at any point. So that's its own special parameter there. For the water pumping losses through the pumps, and I say pumping as virtual because in reality the chilled water is at a high pressure, and this whole thing can just be pressure fed, so to speak, but I still wanted to compensate for a pump just in case I was wrong about that assumption. I used Darcy-Weisbach, Colebrook friction factor equation, and then something called the Woods explicit friction relationship for all of the conceptual design. But I sat down and properly wrote a Newton-Raphson subroutine that solved the Colebrook equation a little bit later, but it never performed quite as quickly. And this equation is almost uniformly a 5% more conservative calculation than even the actual Newton-Raphson, so it was a pretty good initial approximation. Without further ado, here's most of the technical data that inputs into the model. It won't mean very much without spending too much presentation time here staring at it, but it produces this in the heat balance. You get almost a horsepower of heat from both the condensation and the fan losses, but the amount rejected in the final frozen design still has 600 watts of margin on it at the end. And this is just as good a time as any to mention that that margin actually means a lot less, and that this design is even more conservative than you would have seen in this than the previous slide suggested. And the reason why is because even if I did make a mistake somewhere and the heat rejected was lower than what I think it's going to be here, all that's going to happen is that the temperature of the air in the room is going to increase. And as the temperature of the room increases, the relative temperature, the change in temperature between the water and the air also increases. And because of that, the heat exchanger's effectiveness increases as well. And that's not even to take into account the fact that you could have simply increased parameters such as the flow rate of the water, or more importantly, the flow rate of the air. But all of that aside, this is an extremely conservative design. Here's the final design in terms of what it looks like right here. It's 85 inches tall, 43 inches wide, 61 inches long. It needs about 10 gallons per minute of chilled 55 degree Fahrenheit water. It needs about 1 horsepower of fans blowing at 1,500 cubic feet per minute, and that would be satisfactory. It weighs upwards of 800 pounds, fully wet and loaded. It's designed to be able to be moved by a standard tow motor without fork extensions, hence the awkward width of 43 inches. And the manifolds, which are kind of hard to see right now, but I'll break those out in a few slides, can be mounted from either side. They can be fed with water from the top or the bottom, and losses are insignificant compared to the other losses in the system, and I made sure to compensate for that. Regardless of how you choose to hook this up, regardless of how you cap your manifolds and rig this thing, it will still perform as specified. Here's a video which shows exactly how this works. Or rather, here's it to scale. That's a person approximately 6 feet tall, and those pumps are to scale as well, as is this room. Here's the welded structural drawing. It uses 9 3/8 of an inch fasteners without shoulders, and they provide enough clamping force over 7 2-inch angle irons welded to the tops of the 3 square-inch tubes to support the entirety of the heat exchanger subassembly. These are what the copper tubes look like. There are 22 of these stacked on top of each other with an offset of 3 inches. Each one of these is about 18 meters long, or 59 feet each, which does mean that the whole assembly uses more than 1,000 feet of copper pipe. But that's honestly not bad when you're talking about heat exchangers like this. Effectively, the way you assemble this is you don't put this together just like this at all. You thread the straight sections through the plates already fixtured together, and then you braze the turnarounds, the 180-degree U-shaped turnarounds, onto the ends with a can of braze and a blowtorch. Here's the manifold that you couldn't see so well in the assembly earlier. You pick a bottom or a top to it, and you just have your inlet go in and your drain come out in whichever side you want, and you plug the end that you're not using and braze it shut. And that's all of it. Are there any questions?